Okay, welcome everyone to another One Word Mind seminar. It's my pleasure to introduce Stephan Wojtowytsch. Um, he's my very dear colleague and very knowledgeable mathematicians with a lot of experience in various fields throughout the studies. So I'm very looking for his talk in accelerated optimization in machine learning.
All right. Thank you so much for the kind words and the introduction. And yeah, I'll hope that it's enjoyable. Um, Please interrupt me if there's ever a thing that is unclear or that you want to clarify. I have more slides than I'm probably going to get through anyways. So whether we cut it short at half of them or three quarters, same difference. And yeah, I introduced some punctuation to the title that was not on the original announcement, but I hope it'll become interesting. And I'm going to mostly talk about optimization, but for this venue, I feel like at least one brief word of why this is actually interesting in this context was in order. And so this kind of right, this is the oldest problem in science and mathematics, maybe. The I've got or applied mathematics. I've got observations, input output pairs xi yi. I'm trying to predict yi given xi, and I have to make some function class ansatz for what kind of functions I'm choosing. And then this leads me very natural to this kind of optimization problem or something that looks pretty much like it with slight variations on whether we have a square or an absolute value or something more general. And this is one of the standard regression problems that we picture for supervised deep learning, for example, diffusion models, autoencoders. There's a lot of functions that fall into this category. And if h is something that depends on theta linearly, not necessarily on the data, but say polynomials which depend linearly on their coefficients, this is easy to solve directly. We have an explicit formula. But if this is anything that is parameterized in a nonlinear way, say deep neural networks, suddenly this is a much harder optimization problem. And this is the kind of problem that I want to think about for the remainder of this talk. But generally, let's talk a little bit because this is not an optimization specific audience. Let's talk a little bit about optimization and acceleration and specifically what kind of conditions are there for acceleration. So let's talk about gradient-based optimization. What's optimization? Optimization is trying to find typically the highest peak or the lowest minimum in a deepest valley in a landscape. So we're trying to find the maximum and the minimum of a function. And as you can see in this picture, you can make some reasonable guesses, but it is very hard to predict if you just have a general view where those are going to be. And this encapsulates the core difficulty. We have we don't have a good idea of what our landscape looks like. We only have a little bit of perspective. So as a general idea or heuristic of how we think about this, it's typically we think of the objective function f that we are trying to minimize would be the kind of L that I had on the first slide as well, the altitude in a landscape where the horizontal coordinates are given by whatever dimensional x. So this would be latitude, longitude, f would be altitude. And we are trying to find the deepest valley in this landscape. Now, if we were to try to do this in real life, we'd probably try to draw a map of the landscape and then zoom in on the important regions. But if we've got a high dimensional optimization problem, we just can't do that because we hit the curse of dimensionality. If we are trying to grid search or explore our parameter space to any reasonable resolution, we immediately hit the curse of dimensionality, meaning we would need exponentially many grid points in terms of dimension. And there are only like 10 to the 80 particles in the observable universe. So we pretty much immediately get to the point where we can't really do anything brute force in, say, 100-dimensional space. So instead, we choose to not explore the entire parameter space, but only regions that look promising to us. And the general idea that I'm going to follow is to have a particle or person in this landscape who is traveling along a direct trajectory that is supposed to take them to the right places. The most classical one of these trajectories would be the steepest descent or gradient flow method, where essentially we picture a hiker who can't see very far, but we can always look at the ground at our own feet, and we keep walking in the direction of steepest descent and hope that gets us back to the valley. This goes back to roughly 1850. And then we've got a second distinct physical system, which is the momentum method. The physical intuition for that would be we follow a heavy ball that's just rolling down a mountainside. And these are very different physical systems, as we'll see in a little bit. This kind of physical system is what gives rise to the methods that are often called accelerated gradient descent. And I have issues with that name because it's really not the same as gradient descent. It's not just choosing our steps carefully, it's really integrating something like inertia. Anyways, the gradient descent selects locally optimal directions. It's guaranteed to decrease f if we have the continuous time system or if we take small enough steps. And it is incredibly robust. It always works for pretty much any objective to at least decrease the value of the objective function, but it is generally extremely slow. Whereas the momentum method, well, if we have inertia carrying us along our way, we can't instantaneously adapt to new geometric information. We can't instantaneously change our direction of movement, and that means we retain some sort of information along the trajectory. So we have implicitly encoded in the physics a memory of what we have seen before along our path. This may at times increase the objective function f, but there is a total energy that decreases. That is, conservation of energy, dissipation of energy, because we've got some sort of friction here. So in terms of physics, this would be mass is equal to 1. Mass times acceleration is a force. We've got a potential force that drives us to the places where the function f is low. And we've got a friction that takes total energy out of the system. So in some sense, f can behave weirdly, but we'll see that this is actually fast in convex optimization. And both of these methods only rely on first order information of the function f, so only gradients, no Hessians. Nothing like Newton's method. This now is, recall, gradient descent is around 1850. Momentum methods are much, much younger. The probably first momentum method, if you want to think about it like that, is the conjugate gradients method of Hestinus and Siegel in 1952, so roughly a century later, and it only works for quadratic minimizing quadratics or solving linear systems. So these methods can be analyzed very, very similarly. And then about a decade later, we've got Polyak, who uses a specific time discretization of this physical ODE, which is the symplectic Euler scheme. And he proves some convergence for more general functions, but basically the assumption is, well, if you start close enough to a minimum and the Hessian at the global minimum is strictly positive definite, then everything's fine because it kind of looks like a quadratic. And it takes another 2 decades until Yuri Nesterov figures out a proper time discretization, which actually converges at the right rate, which I'm going to make precise in a few slides, for general convex functions. But Yuri Nesterov comes from the optimization community, and this is not immediately linked to what physical system we have. And that doesn't come until roughly 2016 in this paper by Suboid and Candes, which is the the link between the ODE world and restoring that perspective on Nesterov's method. And it's then this whole thing blows up and becomes incredibly impactful in the deep learning community. And there are other things that happen in between. And now we've got a whole lot of other results. There are special classes of convex functions, which are sharp or flat. There are results, well, if I choose my parameters poorly, what kind of convergence do I still get? There's a lot of work on momentum methods, stochastic gradient descent methods, um, some of that by myself and my student Kanan Gupta and our my former colleague Jonathan Siegel, different Siegel, by the way. And then there's new, very recent papers on different kinds of accelerated optimization. So what is acceleration and what do I mean by that in the context of momentum methods? Um, so here we see a trajectory of a ball rolling down a hill. The minimum is somewhere over here, but we see we've got one very steep direction and one flat direction. And in those are precisely the kind of places where we overshoot the minimum, or we overshoot a low objective place because we roll down the mountain and then we roll up on the other side of the valley. And so we get these oscillations that you often see if you're using momentum-based optimizers. That seems bad, but let's look at say this ordinary differential equation system, and I've chosen to have a friction parameter 3 over t. That is because I'm going to look at convex functions. If you had something strongly convex, then you choose a constant friction. But convex functions close to the minimum can become incredibly flat. And if you have a constant friction, you're taking a lot of energy out of the system. And you are taking too much out, which means that you're slowing the whole thing down. You have a weak driving force potentially. And then if you have high viscosity like honey, things are not going to move. So we need something where the friction parameter here actually decays to zero. And the rate is important. And it's not just the 1 over t that's important. The constant 3 here, you can replace by anything that's greater than 3. But if you choose something that's too small, then you may not converge to anything anymore. So definitely if you choose something that's strictly less than 1 as a constant, and you have just any sort of momentum and then you enter a flat region, you will never come to a halt, even if you no longer have gradients, you will just keep rolling forever. So there are some subtleties here. But then Nesterov's a great idea is a specific time discretization. And so let's write this as a first order system. That is also the starting point for Polyak and the heavy ball method. And this system we can discretize, say, by the explicit Euler method. So we've got xn plus 1 is xn plus h times velocity, and we've got vn plus 1 is velocity minus, step size, 3 over time, vn minus gradient f of xn. So this is just the explicit Euler discretization, and we can rewrite that a little bit by combining, the velocity here, we just bring over here. And then we are going to make the choice Tn as n plus 3 times step size. And then we get this n over n plus 3. The plus 3, n plus 3 in the interpretation of time is basically chosen such that this never becomes a negative prefactor, which would be unphysical and weird. Okay, that's just rewriting the Euler method. Nesterov's method now has several innovations. First of all, this is considered basically just an auxiliary step. So we advance by the velocity. Then we do the same thing here with the velocity, but we take a tiny, tiny step here in the direction of the negative gradient. So this happens on a time step scale, scale that is scaled with h squared. So it happens on a much, much faster time scale. It's a tiny time step. It vanishes in the continuum limit because it's a second order correction, but it is a massive difference in discrete time, especially for big step sizes. And then for whatever reason, this is the thing that works. So all I did was shift these brackets from here around the whole thing. That really should make a huge difference when when time n is large, but somehow this is favorable for the analysis. So this is how we get from just an Euler discretization of this system to Nesterov. And yeah, there are slight differences for strongly convex. And from Nesterov, we can also get to Pfister, which is basically you just split the gradients here into an explicit part and an implicit part. But same ideas otherwise. That is the only difference. And that gives us much better stability when we have, say, something that is not smooth and we actually get convergent then. So this is the symplectic Euler scheme. This is what Polyak's heavy ball method does. I forget, I think this is just a quadratic function, and I've done the 3 over t friction. So we see we start here. On the x-axis, we've got time, t, and on the y-axis, we've got the, let's say, position. This is the one-dimensional, just a one-dimensional system. So we release the ball, it starts rolling towards the minimizer at 0, but it has too much velocity, so it overshoots. And then at some point it rolls back, and we've got these oscillations which have asymptotically always the same frequency, but decaying amplitude. So this is Polyak's heavy ball method. It is a very nice, very accurate discretization. This is the forward Euler method. So we see that we make massive, massive errors if we just use the explicit Euler scheme, which is not super surprising. But instead of oscillations getting smaller, we either have them stay is very much of similar size or even increase because the errors accumulate. So, Nesterov, interestingly enough, this discretization is not necessarily any more accurate for the physical system, but it makes the error in the right direction, meaning it overdamps the oscillations. So the term, this gradient descent step, if you look at the second order Taylor expansion, doesn't really give you a more accurate scheme, but it means that the oscillations are now damped too much rather than blowing up in the explicit Euler scheme. And so this is basically a very clever way of making sure that the discrete time system is structure preserving in the optimization way, even if it's not better in the ordinary differential equation solver way. Please stop me, by the way, if there are any questions. And so a lot of the intuition for these optimization problems we can get if we think of quadratic functions where we've got one direction which is very steep, one direction which is very small. And these plots, it's not exactly important what we do in detail, but basically we can think of, well, how much friction do we want in these? And if we do the analysis, we see that we want to choose the amount of friction based on the flat direction. If we if we choose the friction in such a way that the the dampening is optimal for the steep direction, we really, really slow our system down because we don't overshoot anymore. We don't roll up on the wrong side of the valley, but our problem is always going to be making the direction in which we have little gradient information converge fast. And so basically we do overshoot, but that is generally a good thing for us. That is something that makes our optimization work faster. All right. Um, what do I mean by fast? So we've got the gradient flow and we've got the momentum ODE. And then by using some PDE analysis, we can see that PDE, ODE analysis, or a more involved version in discrete time, we can get guaranteed rates of convergence. Sometimes we do better than this, but that's never a guarantee. That depends very much on the function f and further geometric information. But if our gradients are Lipschitz continuous, so L smooth, L Lipschitz, then in the convex case, we get convergence on the order of 1 over n for gradient descent, guaranteed, and 1 over n squared for Nesterov's method. So this is where the massive difference and the massive speedup comes from. This is convex objective functions. We instead of 10,000 iterations, we suddenly only need 100. Instead of a million, we only need 1,000. So there is a huge increase, and the constants in both of these estimates are actually comparable. I think there's maybe a factor of 4 that's bigger in the 1 over n squared one, but there's really nothing that actually makes this worse. And both of these algorithms are implementable under very similar conditions. We have one more vector addition, but the expensive part is always computing the gradients. So both of these algorithms are first order. They only need one gradient per time step. And the hardest part is that for Nesterov's algorithm, if we have a strongly convex function and we want to choose a strictly positive friction, we need to have an idea of the flattest direction. So that's an additional parameter that we'd need to estimate. But if mu is very small, that's which is kind of the typical case. If we have something that's very flat, then even treating it as a convex type, in general, for a long time at least, Nesterov's algorithm is going to still be an improvement, even if we just treat it as a convex instead of a strongly convex function. Asymptotically, gradient descent is going to beat us because it goes to zero exponentially fast, but that is very much the long-term behavior. So this is why we really care, because at least in convex optimization, it works so much better. It converges so much faster. And there are guarantees here that this 1 over n squared rate is actually minimax optimal. Um, I think this goes back to Nemirovsky. The reference is definitely not the original source of this, but if we have any algorithm that works by just adding the gradient at the current iterate and previous gradients, so if we are inside this Krilov subspace, then we will have a lower bound that you can't do better than converging at the rate 1 over n squared in terms of iterations. Slight caveat here, this function lives on R2n, so the dimension is going to come in here. Well, and it kind of has to, because after, if we have an n-dimensional space after n iterations, this is probably going to be the whole space. So we need different lower bounds, different functions for the lower bound, depending on how many iterates we want. However, the function 1 over the rate is not optimal for any fixed function. Namely, it is slightly faster. It is little o of 1 over n squared, not big O of 1 over n squared. And this improvement can't be made quantitative. So we've got this interesting picture where what acceleration means and how fast it is actually depends very subtly on what we mean by acceleration and can we accelerate. And so this is the question that was important to me when I got into this business, because all these guarantees are really nice in convex optimization, but a lot of the time what we're trying to solve is a problem that is not really convex. And well, we can arguably understand that we need some sort of nice structure in our objective functions, because we are keeping a memory of the gradients that we've seen before. We are integrating information from previous time steps into our next time step. And that's only really going to work if our function is not chosen in a crazy adversarial manner. Convexity is clearly sufficient, but many important functions are not convex. So if the set of minimizers is a manifold, if we have symmetry groups, or we have overparameterized machine learning, then the set of minimizers is generally going to be a submanifold if we have this kind of L2 loss, mostly because, well, if I try to solve an overparameterized system of linear equations, I get an affine subspace. And similarly, if I try to solve a nonlinear set of equations overparameterized, then generically the set of minimizers is a submanifold. This goes back to the Morse-Sard theorem, and this holds generically due to the regular value theorem. So this is the issue. But if the set of minimizers is a curved manifold and it is convex, then actually, because the set of minimizers of a convex function is convex itself, we actually end up with something that is, at least locally, an affine space. And generally, that's not the case. So we would like something that allows a little bit more flexibility on the function class for which we can get acceleration guarantees. And this is the thing that I like to picture. We've got a valley. We've got slopes pointing towards the set of minimizers, but because the set of minimizers here, the surface of the water, say, is clearly curved. So this is not going to be a convex set because the set of minimizers is non-convex. But on the other hand, it's really not generically bad. And then we come to the question, well, what's a more general setting where we can still get the same guarantees, the same behavior as in convex optimization? Now, one of the other ways to say, well, my objective function is nice, it doesn't have any strict local minimizers, for example, is the PL condition, which says that the slope is bounded in terms of the height. So basically, if we are not at the minimizer, we are also not going to be flat. We have a valley. This is strictly weaker than strong convexity, and it's not comparable to convexity. So, but in some sense, this gives us a reasonably larger class that allows these curved sets of minimizers. And so we were hoping to get some guarantees under this condition, but unfortunately, there's the article of Yu et al. Where they prove that, Well, if I have any uh, any number of iterations, once again, we prescribe the number of iterations first. Then we say there exists some function f such that any algorithm of this type, any Krylov subspace method, will not perform better than gradient descent on this problem. So this is the exact same rate that gradient descent gives us. We've got a function, we've got a constant here, so we can do better in terms of the constant, but we can't do better in terms of the rate uniformly over the function class. And this is the place where we started our own work. And we made the assumption that this is basically the same as the picture of the valley. We've got a unique closest point projection onto the set of minimizers, and we assume that the convexity, first order convexity condition holds between every point x and its closest point projection. So we only need convexity in direction of the set of minimizers. We call this strong aiming convexity. Um, and we need in discrete time to make stronger assumptions. And there is something that's not written here that's a bigger caveat. We'll get to that. But basically, the idea is, well, as long as we're nicely curved towards the set of minimizers, we get mu strongly convex optimization. And then there's a similar result. Um, I skipped one of them. I'm so sorry. There is another one that proves essentially accelerated convergence is specifically under the PL condition. And there is then this paper of Repchuk and Bumal where they prove these conditions are all equivalent. Theirs is equivalent to ours, um, and at close to the set of minimizers, all of them are at least assuming C2 regularity. Close to the minimum, these conditions are equivalent. So yeah, that these two frames are order reversed. That is the idea that Polyak's heavy ball method does achieve accelerated local rates of convergence. And so at the end of the day, the message is you can whether or not we say we can accelerate for the problem very much depends on what do we mean by accelerate. But convexity is definitely not the end point. It's more, let's say, it's in the middle, and we have not fully figured out what the largest class of functions is. So for the proof, I'm mostly going to say, um, at least in continuous time, you write down a Lyapunov function that is similar to the total energy. So this is the total energy of the system. It's decreasing. This Lyapunov function is decreasing if we have something convex for f, and thus the analysis is basically really a calculus problem. The difficult part is coming up with the right Lyapunov function. For the lower bound, this is the function that you use, and it's built in precisely such a way that in every step, if you use the Krylov subspace construction, if you only use current and past gradients, then you're unable to adjust more than one coordinate at a time, and that gives us slow convergence. And I want to say a little bit, just because I do want to share a little bit of what we actually proved. So we make the assumptions that we've got a linear closest point projection onto the set of minimizers. And that is the big caveat that I was talking about. We do currently need something where the set of minimizers is actually in a fine subspace. It defeats a little bit the motivation, but the analysis is actually already somewhat tricky. So this is still the thing that we proved. And then if the rest of the assumptions is fairly straightforward, we assume that we've got this first order convexity condition with respect to the closest minimizer. We assume that f has Lipschitz continuous gradients, and we assume a lower bound on the Hessian, basically. We don't write out Hessians because we don't have to have C2 functions, but this is basically a lower bound for the Hessian eigenvalues in direction towards the minimizers. This is a negative lower bound for the Hessian in general. And then if we've got stochastic gradient estimates, so if you don't want stochastic optimization, G is just the gradient. Then if we choose our algorithm as a nice modification of Nesterov's algorithm, because things are stochastic, we need to decouple some parameters slightly. So we've got two step sizes, alpha and eta. Eta is this fast time scale, alpha is the slow time scale. Then we still get very, very similar rates of convergence. Specifically, we have the square root mu dependence, and things just get slightly worse in the stochastic case. And with certain kinds of, if we have additive noise, we can't fall below a certain noise threshold. But this is already a significant improvement. We've got fairly general noise scaling, and we no longer are bound to the strongly convex world, but we do already have an indication that beyond convexity, we can get these accelerated rates of convergence. And the proof, in one line, you choose a modification of the previous Lyapunov function, but the trick is that you need something that decouples the movement in direction towards the set of minimizers, so towards the manifold minimizing subspace, and tangential movement. And with this decoupling and figuring out what the correct constants are, everything goes through as previously. So this is our at least first step towards a more realistic setting for more realistic objective functions. And the probably last chapter that I really want to talk about today is the PDE example, because based on this, we figured, well, you maybe don't have the nicest theory, but obviously acceleration can go through in much more general settings than what we understand. So let's look at an example which we can easily visualize, easily analyze, but which is very much not convex. And specifically, we are looking at the Allen-Kahn equation. So the Allen-Kahn equation is a gradient flow, which is based on this kind of energy. Here, we've got two terms. We've got a gradient squared, and we've got an integral of a function of u. So W of u, think of absolute value of u minus 1 squared. So this term, W of u, wants absolute value of u to be close to 1. So W of u, this term wants u to take values just in minus 1, 1. The first term, on the other hand, wants u pretty much constant. We don't want don't want fast transitions. We don't want fast changes. Overall, we've got these two terms, and there is a competition. The trade-off is governed by this small parameter epsilon. In general, we want something that is close to 1 on most of the domain where we're minimizing this. And this is governing what most means. So um, if you do the analysis and you just try to balance things, then you see that what happens is that the function u should be pretty much constant, except for transitions from one potential well to the other, and those transitions happen on the length scale epsilon. This is often called a diffuse perimeter functional because this energy essentially just measures the length of the transition area. So it generally tries to make the interface between the two phases shorter. It converges to a mean curvature flow or curve shortening flow. So here, this is a simulation example for this. Um, we've got the function u encoded in the color. U is equal to 1 is the white phase. U is equal to -1 is the black phase. And then here in between, we've got the transition that is given in red. So this is the boundary curve. And what the energy really wants is to make this this red boundary curve shorter. So it doesn't care about how big the black phase is or how big the white phase is. All it really wants is for there to be as short of an interface as possible. This is a 2D example, compactly supported. This will just go away in finite time. But let's try and look how the Allen-Kahn equation makes this happen. So we see here, we started with relatively sharp corners. Those become a bit smoother. So the corners are being smoothed out. Here, the white phase expands. Here, the white phase becomes smaller. We are just trying to get rid of this. And then ultimately, this becomes convex. And in time, it disappears in a round point. So this is the nicest possible behavior because this is a mean curvature flow in 2D, curve shortening flow, super, super nice analytic properties. So we were then thinking, fair enough, this Allen-Kahn equation is a gradient flow. It's an L2 gradient flow, exactly the same thing that we just argued is kind of slow in convex optimization, and it's much better if we add momentum. So that's what we did. So here you see at the top of the slide the PDE that we're now solving. We've got exactly the same thing, but we added precisely the same momentum term to it. And now let's see what happens. And I think this already looks pretty different because we see that the corners are not nicely smoothed out. The corners still, this one expands, here it contracts. So the corners still do similar things, but we don't get rid of them. We don't actually get higher regularity of the corners here. And at these points here towards the left or basically the center point of the domain, you see that there are some weirdly compressed lines. And this is not an accident. This is where the interfaces are moving fastest suddenly, we get compression. And that is because we fundamentally changed the nature of the PDE that we're solving. By adding this momentum term UTT, we suddenly went from the parabolic world to the hyperbolic world. And in retrospect, everything makes sense, and you see that these transition layers are compressed precisely in the way that you would expect from Lorentz contractions in special relativity. So we have found a system where we see that the momentum method geometry really does something that is strange and different compared to the previous one. And then we get these sort of odd shapes. We see this contracts. This is, I guess, convex at this point, and then eventually it disappears. and then it reappears because we have the geometry where we can roll up on the other side of the valley. And so things become weird. We have a reasonably good understanding of what or why this is happening. We have a singular limit where we let the radius go to zero, and we see that there are two ways we take the limit, and the red lines and the black lines here coincide very nicely. So we believe that we have the correct understanding of this PDE. And it turns out here, um, the the momentum system is not actually the best. At least not if we analyze it in the world of PDEs. We have done additional experiments where we took large time step discretizations. And if we take the gradient flow and the momentum ODE, they look very similar. But with momentum, we get enormously fast movement where the classical gradient flow just becomes stuck. So there is some amount of open problem here, whether the behavior, whether it's just that the continuous time limit is not telling us the best story. But at the very least, this is an example where op acceleration may not be possible if you think about, let's say, these infinite dimensional problems. Um, here we see, let's say, a semi-supervised learning problem. We've got a couple of labeled points, and with just a couple of labeled points, here the gradient flow stagnates a lot more and moves a lot slower, whereas the momentum method works much faster. Once again, with big time steps. So with large time steps and a suitable discretization, we actually get much better convergence, the red line, compared to the green-bluish lines. I think, and this is where we don't have the theory to fully explain that. Um, I think we are nearing time for questions. Let me just briefly mention that I think there is more to that story because there are some interesting new ways of achieving acceleration, and this is very much not my own work, but I think there is a similar phenomenon emerging because imagine that you've got a quadratic form in whatever high dimension. Then if you look at just the gradient descent algorithm, this is this is what it looks like. Next iterate, the vector from the next iterate to the minimizer is just some linear matrix applied to a previous iterate. And you can and gradient descent says, well, we choose the step size. Let's say we're not doing linear algebra, we're doing optimization, we are not exploiting all the linear structure in the problem, but we're just choosing this step size in order to get the best contraction here to make the largest eigenvalue smallest. Linear algebra, yeah, does something a bit fancier. There is, however, an additional idea where you can say, I don't really want to choose the optimal step size in every step. That's too much work, but I'm willing to choose two steps, a longer one and a smaller one, for and what I'm trying to minimize is actually the norm of the product. And then I alternate, I take one long step, one short step, one long step, one short step. And this makes a lot of sense that this should be much better because the long step, well, it helps me in the direction of the smallest eigenvalue. I need to take long steps to get anywhere here. The long step on the other hand, it does break things for my largest eigenvalue, which is bad, but then I'm taking another step, and the direction of the largest eigenvalue, the steep directions, well, I have lots of gradient information here. I can repair that with a small step. I don't need a whole lot. And so it's much better to have two step sizes compared to just one. And then this goes back to like 53. So we've got a rate of convergence which is precise, which works better, and you need a step size schedule there. And then much more recently, we've got a bunch of works on the silver step size schedule, where we have an interesting separation where gradient descent converges with this 1 minus kappa rate, where kappa is a very small constant. Nesterov gets to 1 minus square root kappa, square root kappa being much larger. And this silver step size, where you don't change the algorithm, actually converges to it converges at a rate that is somewhere between the two. Instead of power 1 or power 0.5, you get the power 0.78. This, by the way, requires not just two step sizes, but a sequence of them. But so yeah, I think there's an interesting analogy, because obviously with Nesterov's method, we do occasionally see increase. The same happens here, but overall, we can sometimes afford to overshoot in the steep directions because that's easy to correct later. But what's difficult is we are trying to make progress in the flat directions, and that is something that we can do better if we allow ourselves to sometimes take larger steps. So I guess a weird takeaway for me, at least initially, was that we should embrace this non-monotonicity because we do get faster convergence for it. And so, conclusion, acceleration is a really powerful tool in gradient-based optimization. It does have this non-monotonicity, which seems to be necessary, although I've not seen any rigorous statement saying if you're monotone, you can't accelerate. It requires obviously some sort of nice geometry of the function that we're trying to optimize. Convexity is enough, but it's not really necessary. But in non-convex optimization, I still do believe that there are scenarios where momentum may not be the right idea. And I'm not even sure whether non-convexity is necessary, because similar things I imagine hold just for the pure Dirichlet energy, because really what we get is this hyperbolic behavior. So yeah, this is my story of acceleration is a great tool, not a one size fits all tool, and it does work in a wider set of problems than what we typically consider, but it may not work everywhere. All right, and thank you so much for your attention. These are the things that this is based on, and please let me know if there's any questions.
Okay, thank you very much, Stefan, for the very nice talk, and also didn't fail my introduction of you being knowledgeable because you cite a lot of old papers. That was my expectation.